Now understand what is linear regressions. Our name says it is a linear plus regression. It means we will be getting an output in the form of straight line showing the dependency of one variable to other. If we take a definition per se, linear, it means extending a straight line is nearly a straight line, and regression is a technique that determines a relationship between two or more variables, where change of a variable is causing an effect or change in another variable. So we are saying what we are creating a ecosystem to validate the relationship of one variable on another. Let me take one example. Say we are having one x variable, and this is my y variable. So suppose if I am having data like this, so it means we can easily say the change in x is triggering change in y, and we can easily this is a sort of linear data, and respective change can be represented via a straight line like this. So linear regression is an algorithm to get this linear line showing the dependencies of independent variables on dependent variables. So if I take example, so we are taking the proportions. So the slope of this line would be decided based on the how much of change. So I say delta of y versus delta of x. This ratio determines the slope of this line. So if you are in this case, we are seeing a more or less equal proportion is there in terms of increment. If I say my line is likewise, let me draw one more line. Say if my line is this one, blue one. So in that case, I can easily see that a small change in y is proportional to the larger change of x. So you can say change in x, the larger change in x is impacting lower amount in y. Sorry. So if I change a larger value in x, the impact of the change will be very minimal on y. Parallelly, if I take a line like this, here the case would be vice versa. Small change in x will trigger higher change in y. Let's take an example. So if I change this portion of x, this portion of y will get affected. So slope is showing the relationship of your one variable to another. So I can say this is my independent variables, and this is my dependent variable. So I am looking for one equation which could be predicted y equal to slope of x into intercept. Let me add b. Yes. So this slope is nothing but is a proportion of this ratio, and b is if you take this red line example, it is nothing like the interception of red line, where my x is 0, I am having some y value there. So this slope is delta of y versus delta of x, and b is my intercept. So I am interested in getting the equation of this linear regression. For that purpose only we are seeing. So regression is an attempt to explain the variation in a dependent variables using variation in independent variables. So my this equation of linear regression would be getting equation in such a way that I am able to get the relationship represent in such a way that if somebody asks me to predict some value of y based on a given value of x, I can easily predict the value of y based on value given x if I have this equation. So last point, if you see, if the independent variables significantly sufficiently explain the variation in the dependent variable, the model can be used for predictions. And so we are saying both the values are correlated, or you can say they are impacting to each other in a more significant way. So prediction can be done. So before going for prediction, let's see one concept there. I'll say first and foremost thing we have to make sure we know this concept of correlation. Correlation is what is a cause and effect relation. So if I say if I have data like this, so I say here we are saying it's a positive correlation. A change of x is triggering a more or less proportionate change in y. So here we can say it's a positive correlation. If you get data like this, data like it's a change of x in positive is a negative change in y. So we can say our relationship is correlation. C can trigger correlation. More higher correlation in two variables, the prediction would be really good. If you are in lower correlation, it could be a positive negative correlation. If you are having higher correlation, higher absolute correlation value, the prediction would be high. So if you are saying, I don't have any relationship in my variables, so my correlation would be near to 0. So if I say my data is like this, I'm not able to showcase any relationship because there is no relationship. Even any change in x is not impacting in parallel proportion of y. So it's, you can say, near to 0. So we can say correlation value would be between positive 1 to negative 1. So any value beyond 1, any value near to 1, either in positive or in negative term, is good for prediction. Any value near to 0, that's going beyond 1, and going near to 0 is bad for as prediction. So it's a thumb rule. Value near to absolute near to 1 is good for prediction. Near to 1 means it can be near to positive 1 or it can be near to negative 1 also. So if you say, let me go beyond, value near to 0 is bad for prediction. So that's a thumb rule which we have to take care while making a prediction starting. So in correlation, we are saying we are having a logical formula of correlation is likewise. So I say R. If we take a normal case, it would be like this: summation of x minus x mean into y minus y mean. So it would be summation of x minus x mean into y minus y mean divided by, I'll say it is square root of summation of x minus x mean square into summation of y minus y mean square. Summation of y minus y mean square. That's a formula. It give you a value within the range of -1 to +1. So we are happy if I get data in near to 1. Any value near to 0 is bad for us. So this value beyond 1 is good for us, and any value near to 0 is bad for us. Any value near to 1 is good for us, any value near to 0 is bad for us. So collision points, your collision score should be near to 1. If you are having your value correlated to each other, you will be getting higher correlation as compared to non-correlated values. So linear regression having a proportion of correlation in their prediction part. So if data is correlated, you might be getting higher correlations, higher prediction values, higher accuracy value, you can say. So thereafter we are saying if for making this equation, so we require, say for making my linear equation, which is predicted y is equal to a x and b. Now x is my variable, so I don't have any formula for this. I'll be getting value from user, so I'll be working on a and b. So let's see what is the formula of getting this slope. Slope is nothing but you are saying you are getting a delta of y versus delta of x. So indirectly you say as we calculate r into, so we are saying is standard deviation of x, or standard deviation of y versus standard deviation of x. So if we say what is standard deviation formula, so it is nothing like if you say summation of y minus y mean square and minus 1. Parallelly for x, formula would be like this: square root of x minus x mean divided by n minus 1. So via this you will be getting this a score. A is slope. So if you are having a, you can get your b value. So b is what? B is nothing, but you can say it's a score. This is mean of y minus slope, which you get in above formula, into your mean of x. So this is my b. So this we call intercept. Intercept. So as we got both the slope and intercept, we can make an equation for predicting y. So in linear regression, we are having a few concepts which we have to take care before going to the coding part of Python. So let's see, we are having few terms there. Say as equation we are having, where b0 is my intercept and b1 is my slope. So important terms which we have to take care: the correlation which I had already seen, standardization is formula we had already seen, slope we had already calculated, intercept we had already calculated, and let's go for standard error. Standard error is, let me take one line there. So standard error we are writing like this, E notation. Let me take a different color. It is nothing but is a difference between your actual data versus original data, actual data versus predicted data. You can say this is y minus predicted y. This is standard error. Standard error. Or we can say like this. Let me write it in normal way. Or we can say residuals are there. We can call it residuals also, depending on case, whatever you call it. So it's nothing but it's a gap between predicted versus actual. So if you take an example, so let me make one chart here parallelly so that we can take the case. So I take this is my y-axis and this is my x-axis. I'm having few values like this, and I got a linear regression like this. So my error would be the gap of predicted versus actual. This is my gap, is my standard error. So in technical terms, we can say as a rule. So we are saying all the summation of is near to 0 and even mean of standard error is also near to 0. These are the standard error which you have to take care. So my motto is to reduce my standard error to get the most preferred linear regressions. So next, let me see what is next. So we are having standard error. So linear regression equation we had already taken. So that would be like, so let me write down linear regression equation. So let me color in some. So this is what we had already done. So this is y. I should say predicted y, hat y. The slope, which the formula we had taken already, into your x. The x variable, let me take x as in other color. Then we are having plus intercept. Intercept. That's my linear regression equations. So as we got the slope and intercept are there with us, which I calculated earlier, so we can make a linear regression lines. So henceforth we'll be more focused on getting this values from this predicted y. So we are having few figures which we have to take care. So let me take one case. This is the case of sum of square error. So let me write down this here. This is nothing but summation of actual y versus your predicted y, the square of this. So it's indicate what is the difference between our actual value and versus predicted value. That's a case which we are looking for getting this data value. Then we are having some other formulas. Let's go for that also. So we are having this sum of regressions, sum of square of regressions. So for that, let me copy this also. This is nothing but we are getting a difference between your predicted value versus mean. Let me take it in some other color. So I say it is sum of predicted y minus mean of y. Then we are taking the square of this. That's a sum of square regression. So next value we are having with us is the sum of square total. Sum of square total is let me take a small gap. So this is we are having is your gap of your y's, which is actual y's versus mean of y. So based on these values, we are getting one output which is R score, R square score. This is we write like this, R square. The score indicate how good is your linear line to represent your actual data points. So it can be, you can write like this, your data SSR versus SST. So it generally come between 0 to 1. So any value near to 1 is good too, showing that your linear regression is good and is representing your most of the data points. If it is near to 0, it's bad for us.